Police use radar to detect speeding cars. A police officer stands at the side of the road, points a radar device at an approaching car. Let's draw a picture of this. Here's the car. Moving this way, the police officer's standing here. Pointed at the car, right? Basically what happens is that these radar signals come off of here. They are perceived by this car or hit by this car. And there's, by the way, a Doppler shift because of moving observer, right? Moving observer. And then when they reflect back, because they're reflecting off of something that's moving, you also have moving source. Okay. Now, because light is relative, right? In fact, this is the basis of like special relativity and time dilation and all this crazy stuff, right? The formula for light, for moving observer, moving source, is the same, because the whole principle of light waves is that they're always traveling the speed of light. But their wavelength can shift because of the motion of this, right? So explain the reason for this frequency change. Talk about the Doppler effect, right? Also, you can talk about how it, receives the thing as an observer and also as a source. But that's what they're getting at here, right? Why is there a factor of 2? Because this, by the way, is without the factor of 2 is just this what you would observe. Okay, and it's an approximate formula. There's a better formula. They're just not giving it to us. Okay. But the factor of 2 is because there's 2 shifts going on. There's the moving observer, and then there's the moving source. Okay. So explain the reason that has to do with Doppler and such, right? And then explain why there's a factor of 2 is because it's both observer and source, and light is just, it's all the same, right? So, and by the way, if it was just what frequency is observed by the car, the shift in frequency would be just frequency times that velocity over the speed of light. This is a very approximate formula, by the way. All right, good enough.